Lifeblood is a task management software package. It lets you process arbitrary tasks with logic defined by nodes and driven by task attributes. This tutorial is of a very particular application. It doesn't go into details or logic of Lifeblood. It shows you how to use one of predefined setups. It may be better to see some practical examples before diving into theory. I suggest first looking at some other basic tutorials on caching, wedging and rendering before watching this one to have some basic intuitive understanding of how Lifeblood works. In this tutorial we will take a look at the default Houdini flip distributed simulation setup. From Lifeblood's side, the preset is not specific to flip. It can work with any Houdini's distributed simulations if task creation process is adjusted properly. A quick reminder about Houdini's distributed simulations. Houdini has a way of running some simulations, such as Flip and Pyro, distributed over several computers. This is done by splitting the main task into slices, parts of original problem, that are solved usually for one time step on different machines independently. Then slices synchronize and exchange border information over network, then next time step is solved, and so on. This setup requires a way for slices to synchronize after each slice has finished its time step. The way it's done in Houdini is with a special dedicated lightweight server called tracker. So a tracker needs to be running, and all slices need to know its address in order for distributed simulation to run. Obviously, there is no point distributing simulation in a way where all slices run on the same computer. It's way better to just compute the whole simulation without distributing it. Slicing is not efficient and may produce undersolved artifacts on slice borders. It is somewhat of a last resort that you do only when you really have to. For the sake of this tutorial, I could still run all slices of a distributed simulation on the same machine, but let's make it more real and add another computer. As you see, there are two computers with shared network folders are currently running local worker pools each. On Houdini's side, we will create a shelf setup with water being emitted from the sphere. So this will be our setup to be distributed. Maybe we can add a bit of separation on it. We will split this simulation in just two slices, since we have two physical machines, but we could easily make more of them. And now we will just call the standard Houdini distribution tool. And we choose the method of slicing as opposed to method of not partitioning and cancel. As a result, it will create a HQ node, but we don't need it, so we will just delete it. Now let's create a Lifeblood node. Now here in Lifeblood we will select the preset called distributed flip, which will do most of the work for us. It comes almost ready to go for the default shelf distribution setup. Here are three nodes that you have to specify for it. The flip object node, the distribution control node that default setup creates, and the save caches node. The preset values actually are set to the values that you will most probably get when creating the setup from shelf. So you see they're all pointing to the correct nodes already. But if not, you will just need to adjust these paths. There's also a handy button here. When all paths above are correct, it will make all the changes to the default setup for it to run with Lifeblood. So let's press it. Now we're actually ready to start the simulation. But let's quickly go through the changes that the button made. First, it set the tracker address and port on the simulation control node to context attributes that Lifeblood will set when running the slices. Second, on the save slices node, or actually on load slices node, it will change the default slice variable here to lbutter slice. By default, all task attributes are available in Houdini or in any other program running as lbutter underscore attribute name environment variable when the task is being executed. Slice is the name of the attribute that will be created on the task in Lifeblood setup, and we use it here. The context variables, like the ones set on the control node, are also set by Lifeblood, but that's a feature of the heap driver Lifeblood node specifically. We will see it a bit later. So why mixing? Why not using context attributes here as well? Generally, I prefer use the context attributes, but in this case, using environment variable is just more handy. It requires less changes to this setup. Now let's take a look at Lifeblood side. Here we will start with the default flip distribution preset. It all starts with a null as usual. Then we have a create sim tracker node. This node will start Houdini's standard simulation tracker server. When the tracker is started, it will create a child with actual tracker's IP and port to be used by slices. This node will create a task for each slice, and then this heap driver will simulate the slices, schedule slices for simulation. And here note that task attributes slice and simtracker underscore asterisk will be set as context attributes in Houdini session, so they will be available as @attribute name. After that, there is just some synchronizing and waiting. Stop simulation tracker node will send the kill signal to the simulation tracker, knowing its kill port. And here the original task will synchronize with its child, and that is it. Let us now run it. We are ready here. All we need to do is to listen to the broadcast to set up the scheduler address. Save the scene and let's go. Now you can see that the slices were picked by different machines with different IP addresses, and the resource requirements are set in a way that each slice will consume all the resources available by the machine. Well, actually, you can see that it's set to consume some big value of resources, which in this case takes all the resources of the machine. The resource requirements in Lifeblood in general works in this way. You have the minimum required amount of resources and the preferred one. So the task will be submitted to the machine that has at least this amount of cores, but it will actually take all the way up to 32 if available. Same for the RAM. It will require at least 1 GB of RAM, but it will take up to 128. Not take, reserve for the task. In this case, as we see, all 64 GB of RAM were taken on one machine and all 32 GB were taken on the second, as well as all the CPU cores. Now let's just wait. Also note that with equal slices the simulation will run with the speed of the slowest machine. In my case, the second machine is pretty slow, but on top of that they are synchronizing over a ridiculously slow Wi-Fi network. It's not that Wi-Fi is bad in general, it's my particular Wi-Fi that is bad. Now as it going on, let's check the cache that's being created. Now let's take a look at individual cache slices just to be sure. So these are points from slice 0 and points from slice 1. Now, as a bonus, why not add in a meshing to our setup? We will start from standard caching preset, and here we will just change the frame chunk size to just 1, so it will be 1 frame per task. And here we will not use the requirements from slice simulation, instead we will put in something arbitrary. And the heap driver, sure, we could add another parameter to Lifeblood submitter to have path to the surface cache node in an attribute, but let's do something simpler here. We know that in heap driver in a task we will have path to the save slices node, and we need a node called surface cache that is just in the same parent node as this. So we make a little expression here. And remember that we need to put the path to the inner rope geometry node, not to the file cache node itself. And it should be good to go. We just connect the cache preset to the distributed simulation preset and wait for the distributed simulation to finish. Now you see caching will be done much faster. Surfacing will be done much faster. Now we can go to our scene and see the result of the cache, but loaded from disk. Some frames are already surfaced and cached. For some of them we will have to wait. And now it's all done. Distributed simulation was computed and surfaced. Now, as you can imagine, we can add any kind of arbitrary processing after, maybe a test render, notifications, or a report to some project management software, well, whatever you want. But for this tutorial, we are done.